So far we talk about the cosmological perturbation, how the inhomogeneities in the universe evolve over the cosmic history. We first of all classify the two regime, Newtonian one, and the general relative theory, and we simplify the condition with the superhorizon limit and adiabatic condition, and we talk about the matter perturbation and the radiation perturbation. And now I talk about how the initial primordial fluctuation delta I arise, and these primordial fluctuations are generated during the inflation approach in the extremely early universe with the quantum fluctuation. And these primordial fluctuations will be the seed of the large-scale structures like as the CMB or the matter pulse spectrum. And from the CMB anisotropy, we know the density perturbations has order of the 10 to the minus 5. And such density perturbations are initially starting from the Inflaton field pi. This Inflaton field pi satisfies the following equation of the motion in the expanding universe. We can perturb such scalar fields over the background. Then this perturbing Inflaton field satisfies the following dynamics. This is just the burst order, and the right-hand side includes the metric perturbation. The presence of the metric perturbations meaning that the Inflaton field fluctuations is not gas invariant, but this is a physical quantity. We want to define the gas invariant quantity. Already we talked about the metric perturbation, especially the scalar component. And we assume that the Newtonian gauge choice. Then scalar perturbations are written as the following form for the metric. Then we can define the gas invariant combination, which is called the co-moving curvature perturbation (CLR), as combinations of the scalar perturbation, Hubble parameters, and the Inflaton field. Then we can expand the Einstein action, including the Inflaton scalar field, as a second order. Then among this expansion, we'll take the quadratic term. Then this term will include the gauge invariant curvature perturbation (CLR) with the R prime, the conformal time derivatives, and the gradient curl R, partial derivatives with the variable z. The z is the defined for convenience, which is called the Mukharov-Sasaki variable, and also for the v. This process is just the reformations of the Inflaton field fluctuation in terms of the gauge invariant quantity, especially the curvature perturbation (CLR). By using these variable changes, the second order action takes the following form. Then this yields the following equations of the motion in terms of the v and the z. So z is the replacement of the scale factors, and the v is a replacement of the CLR, the curvature perturbation. We can observe that this equation is just a harmonious light form with the time-dependent frequency. For the superhorizon limit, the equations are reduced by just a simple harmonious light. Because the K inverse is smaller than some specific scale. So this is correspond to the superhorizon limit. And now the frequencies become time independent. So this has just a simple oscillator solution. But if we consider super horizon limit, k inverse is larger than some specific scale, then the effective frequency becomes the time dependence and is partially imaginary, which gives the breathing of the curvature perturbation. So the curly R or V got just a constant solution. So we only just talk about the Inflaton fluctuations formulations written by the curly R. But now we will add the quantum effect. The quantity V can be promoted to the quantum operators and expanded still with the Brien mode. So that this V becomes a quantum operator still with the head notation. And there will be the annihilation and creation operator at each Brien mode. This allows the operator to satisfy the commutative relation and also taking the time dependence inside of this operator. The coefficient becomes a time dependent one, so-called a mode function at each k mode. Now there will be some interesting behaviors that appear. Because the universe get the expansion, the vacuums is a non-unique because the Hamiltonians now becomes the time dependence. So the vacuums at the specific time and the other moments are the different. So we should connect the different vacuums at each moment. One can consider the earlier time limit so that the some specific given mode is inside of the sub-horizon. In that region, the mode equation is just reduced by the simple number which light radii I mentioned. So in this limit, k is equal to infinity, the mode functions are just given by the oscillator. This choice defines some specific vacuum, so-called the Burns-Davis vacuum. Under the slow approximation, the equations of groups are reduced as the following form. The second terms are just given by the function of the complement time tau. The solutions for these approximations get the following form. Now there will be some correction in Poulon's of the oscillation. So this means that the solutions of this quantity V replacements of the curly R get the non-trivial solution. And we promote this V as a quantum operator. If we consider early time limits again, then these solutions are reduced to the Burns-Davis vacuum. It is constant with the general solution. But if we taking the opposite light time limit, so the k mode, so outside of the horizon, then the domino the behaviors inside of the general solutions are just given by the one of the tau. So by replacing ones to the curly R, the curvature perturbations again, then and using the relation between the time variable, complement time tau, scale factors A and the new variable Z, then we can find the curvature perturbations that get the constant values at the right time. This implies that the perturbations that breathe, no oscillations, no growth or no changes after the specific k modes that exist over the horizon. So this is overall behavior. So if we take the imaginary sort of the curvature perturbation called R, when the specific k mode is the inside of the horizon, they get oscillation behavior. But after this k modes that exit the horizon side, then the curvature perturbations are just frozen, get the constant solution. So let's summarize what we have discussed now. So we think about the inflation fluctuation delta pi, consider the initial fluctuation, and we analyze together with the matrix perturbations and the gauge invariant quantity, curvature perturbation curly R. And we replace some variable, Mukhanov-Sasaki variable, V instead of the curvature perturbation curly R. Then dynamics becomes the simpler which lattice with the time-dependent frequency. In the superposed regimes, the mode behaviors show that oscillating solution, but when the K modes outside the horizon, the curvature perturbations get just a constant value. And also the V quantizing this V, the Mukhanov-Sasaki variable as continuous lattice, and impose the Burns-Davies vacuum. And we select the initial state of the fluctuation, then each mode functions correspond to the amplitudes of the primordial perturbation. So we will define the quantum operators of this Mukhanov-Sasaki variable V with each Fourier component. By taking the vacuum expectation value, then one can obtain the power spectrum from this quantity V. This is just a similar step when we extract the power spectrum from the CMB. So quantum barriers of each modes are represented by the power spectrum now. But the physical variable is the curvature perturbation, curly R, not J or V. So now we can relate the power spectrum in terms of the curvature perturbation, P curly R. Also, this P curly R is related with the real space variable, the variance of the curvature perturbation, curly R, with the Fourier transforms relation. Then the dimensionless power spectrums can be defined as K cubed over the 2 pi squared times the P curly R, which is integrated over the L and K interval. So now we will define this dimensionless power spectrum as a delta curly R. So now we get the initial perturbation from the Inflaton fluctuations at the very initial approach. Then how do these power spectrums evolve? We can insert this Burns-Davies mode function inside of the superhorizon limits at the initial time, not the initial time, though it's the superhorizon limit. Then during the evolutions, one can obtain how this dimensionless power spectrum delta curly R's evolve over the time. So this was the solution in the superhorizon limit. And we will rewrite the time variable Z in terms of the other variable is partially conformal time tau. And we know the relation between this dimensionless power spectrum delta R and the Mukhanov-Sasaki variable V. And we know the solution, then we can insert this. Then the final results of this dimensionless power spectrum evolutions are just given by in terms of the Hubble parameters and the π. This is a main final result. Also, we can relate this fluctuation directly to the Inflaton perturbation delta R, because this curvature perturbation is related with the delta pi with the following relation. Then by considering the variable changes, then the power spectrums of this Inflaton perturbation delta pi are just given by the h over 2 pi overall scale. So the results is the following. So Inflaton fluctuation and the curvature perturbations are related by the following relation. Curvature perturbation curly R and the Inflaton fluctuation delta pi also released for the power spectrum. So during the inflations, the quantum fluctuations of the Inflaton field and the metric in terms of the Curly-R, generalize the initial fluctuation, the primordial perturbation. These color perturbations are typically described by the gauge invariant quantity, which is curvature perturbation Curly-R, and this dynamics is written by the Markov-Sasaki equation introducing the canonical variable V. And we promote this V as the quantum operator, and the dynamics is just given by the harmonic oscillator through the time-dependent frequency. And we found the solutions that behaves like that. It oscillates inside the horizon, but breathes out. It got the constant behavior. And the quantizing the V, and we impose the Boone-Davis spectrum as initial quantum state, and we can determine the amplitude of the fluctuation and how the dimensionless power spectrums evolve, and given how is the given as the primordial fluctuation. So, as a long story for this cosmological perturbation series, we watch the Newtonian and the zero regime, and we make the simplification with the superposition adiabatic condition, and we apply the methods and the radiation component, and today we talk about the initial fluctuations, how this is generated during the inflation. And in the next video, as the final topics of this cosmological perturbation, I'll talk about what is the observational quantity for the CMB or the inflation related quantity.